Can you hear me? Okay. Okay. Thank you very much for inviting me to give a tutorial here, and also for the very kind introduction. Now, I just borrowed something from David Shea. Okay. Well, some of you may notice that now I also have a new affiliation called Institute of Network Coding. The story was that at the Chinese university, we managed to get a grant to set up such a research institute. And I learned it from David Shea. Any good show starts with a commercial. So now, for this Institute of Network Coding, we have some postdoc positions available. And if you're interested in such positions, please contact me. And we don't limit ourselves to candidates with prior research experience in network coding, because our aim is to build a team consisting of people with diverse background with the aim to make network coding work. Okay, this talk I'm going to talk about multi-source network coding. This will be one of the few talks that you have been to on network coding that doesn't talk about the butterfly network, nor the cockroach network that I learned about this morning. Now, instead, I'm going to start with a historical perspective on the problem. After I finished making up the slides, I found that the contents of this tutorial is not very consistent with the abstract, because I found that it takes a long time for me to talk about some of the details. So instead of talking about other things, I would try to go straight to the heart of the problem. And at the end, I'll make some remark on what we are currently interested in. Okay, first we start with the seminal paper by Claude Shannon in 1948 that brought us all here today. Now, in this paper, Shannon said that information is about uncertainty, and for efficient transmission, information should be compressed into fair bits. Fair bits means IID bits which are equally likely to be 0 and 1. And fair bits can sort of be regarded as atoms of information. It's not a very precise statement. That's why I put things in quotation. And also that the message that we got from Shannon's work was that fair bits enhanced information can be kind of regarded as a commodity for point-to-point communications. Okay, so this is some of the essential things that we learned from Shannon in his 1948 work. And there's a reason for me to put these few words in gray instead of in black, as I'm going to explain. Now, this commodity flow view was inherited by the telecommunication industry, namely in the telephone industry and also in the internet that follows. Now, I'm going to talk about the first inspiration, or how the idea of network coding came about. Now, we look at this a distributed storage problem. Okay, so you think of these cylinders as a disk where you can store some information. We have an information source X, which are stored in some coded and distributed manner among these disks. And these are nodes that have access to some of the disk, okay, in some arbitrary ways. And the goal is that for all of these nodes, they would be able to reproduce the information source X exactly. And here's an easy solution. Okay, to characterize the problem, we only have to say that the bandwidth, the incoming bandwidth for each node is at least equal to the size of the information source X. And this can be realized by means of an MDS code, for example, a Reed-Solomon code. Right? So that's an easy solution. So now let's take a look at a more elaborate situation. In this case, we have 3 disks, okay, and we have 2 information sources X and Y, and we assume that X and Y are independent. Now, at the bottom, we have 4 nodes, each with its own connectivity, but they have different reconstruction requirement. The node on the left-hand side can recover X, while all the other 3 nodes can recover X and Y. So we ask, what is the necessary and sufficient condition for this to be possible. Let's see. Oops, did I miss something? Okay. I think I missed one slide. Okay. So I'll explain this in words. So again, this is a very easy. You have a very easy solution. What you do is you put x. Let's assume that x and y are just binary symbols. What you do is you put x here on the left. You put y here in the middle, and then you put x plus y on the right-hand side. So this node, by accessing the first disk, would be able to recover x. The other disk, the other nodes, for example, this node can recover x from here and y from here. This node can recover x from here, and upon knowing x plus y, it can also reconstruct y. Okay, so it's a very simple solution, but that's not the end of the story. It turns out that this is only the beginning of the story. Now, the question we have in mind is the following. Now, we have two sources that are statistically independent. We want to ask whether it is possible to separate the coding of these two sources. Namely that we want to see whether this problem can be decomposed into this subproblem and this subproblem. Now, this subproblem means it's the one that we look only at the x source. Okay? So x is being here on the top, and then they have to be reproduced at each of the 4 nodes. Okay? And this is the subproblem associated with the y source. Okay? Y is on the top, and at the bottom, y is to be reproduced only by the 3 nodes on the right-hand side. Okay? So the question is, for any solution to this problem, is it always possible to decompose it into 2 parts such that one part is the solution to this problem, and then the other part is the solution of the other problem? Okay? And then on the other hand, if we can solve this problem and this problem by putting the two solutions together, we would be able to have a solution for this problem. So the question is to ask whether these 2 problems are the same problem or not. Now, this is it turns out that the problem is not source separable in the sense that I have just explained to you. Now, the implication is the following. Imagine that we try to communicate on the internet. Okay, let's say I try to send out a message in Chinese, and you try to send out a message in English, and what we try to say have nothing to do with each other. Statistically, they're independent. But it turns out that in some situation, it is necessary to jointly encode the Chinese message and the English message somewhere in the network in order to achieve bandwidth optimality. So this is perhaps the first evidence that in network communication, it is not sufficient to regard information as a commodity. Okay, why is this intriguing? Now, if you don't know anything about classical information theory, this may not be something very intriguing to you. For example, it's not something very intriguing to my wife and my daughter. Now, let's consider this situation in which we want to communicate from one point to another point. Now, on the left-hand side, we generate 2 information sources, x and y. If we compress x by itself, then it takes about h of x number of bits, approximately. And if we compress y by itself, it takes entropy of y number of bits, approximately. On the other hand, if we compress them jointly, then it takes this number of bits, approximately. Now, however, when x and y are independent, we know this inequality, which says that entropy of x and y is equal to entropy of x plus entropy of y. Okay? So it means that asymptotically, whether you compress the 2 sources separately and then you send out the cowords together, or you compress the source jointly and send out one coword, it doesn't matter asymptotically. Okay? You are doing the same thing. Now, so for point-to-point communication, there's no multi-source problem in the asymptotic case. In fact, we have not. We rarely hear about a multi-source problem in data compression because asymptotically, whether you regard them as one source or multiple source, it doesn't make any difference. Now, the thing is that so we have seen that for source for point-to-point communication, source separation hold asymptotically. However, the intriguing thing is that this does not generalize to networks. Okay, that's the first message I would like to get over. Now, this example actually was once this example here, okay, was first discussed in a paper I wrote in 1995, and from that point on, I got very interested in communicating multiple source in a network, and that's perhaps is the first inspiration on the eventual discovery of network coding. Okay, here's another example, which is very easy to understand, but it didn't come about in the mid-90s, but it came about in the early 2000s by various people independently. So in this example, we have two nodes, one node on the left and one node on the right, each generating one bit, B1 on the left and B2 on the right. So if we try to exchange the 2 bits over the network, this is what we can do. Now, traditionally, we would think of this task being 2 independent tasks. The first task is to move bit 1 from left to right, and the second task is to move bit 2 from right to left. If you want to move bit 1 from left to right, okay, this is essentially the only solution. Okay, you just go through this path. This is the only path that connects from you from the left node to the right node. Okay, whether you do any coding or not, it actually doesn't matter. So basically, you just route B1 through the network to the right-hand side. And likewise, the only thing you can do is, if you stick with the routing paradigm, the only thing that you can do is to just route B2 from right to left like this way. Now, by doing it this way, we need to transmit 2 bits from the top node to the bottom node. Now, after seeing some of you have seen the butterfly network and things like that, and after seeing the butterfly network solution, it is not difficult for you to come up with this solution, namely that you send B1 up here and send B2 up here. Upon receiving B1 and B2, you just add up the 2 bits in modulo 2, and then one copy goes here and the other copy goes here. Now, this node, assuming that it still remembers its own bit, can recover the value of the other bit by receiving B1 plus B2, because B1 plus B2 essentially tells you whether your bit is the same bit as the other bit. Okay, so by symmetry, this guy can also recover B1. Now, this example actually has a wireless or satellite interpretation, because if you look at this part of the network, it actually mimics a broadcast channel, because in a broadcast channel, whatever you say is heard by everyone within the line of sight. Okay, so this, you can think of this being a dummy node. Okay, and by first sending a bit to this dummy node, you kind of force the value on this channel and the value on this channel to be the same value. Okay, so this is essentially the idea. Now, with this, we have a wireless application of network coding. So there are 3 nodes here with the bit B1 generated on the left and the bit B2 generated on the right. And they need to exchange the 2 bits through the relay node in between. So the traditional method is to do it by routing, namely that it takes 4 time slots to complete the transaction. First, you send B1 from left to middle, and then from middle to right, and then you send bit 2 from right to middle, and then from middle to left. Now, after seeing the previous network coding example, this is something better to do. In time 1, you send B1 from left to right, from left to middle, and then you send B2 from, and then in time 2, you send B2 from right to middle. And at time 3, you simply broadcast the modulo 2 sum of the 2 bits. And this is to take advantage of the broadcasting nature of a wireless node. And with this very simple coding, you save 50% for the downlink bandwidth. So the saving is quite significant. Now, is this a violation of classical information theory. Actually, it's not, because classical information theory only says that the commodity flow paradigm applies to point-to-point communication. It didn't say anything beyond that, although for a long time we tend to think of it that way. In fact, it was a folklore for decades that the commodity flow paradigm is optimal for network communications. Now, we are now talking about a model which is a step toward multi-source network coding. So this is a model that we studied in the late 90s. It's called a satellite communication model. We have a number of ground stations here, and then we have a number of satellites up in the sky. Now, each ground station could be a transmitter or a receiver. For the ground transmitter, each of them can transmit to more than one satellite. As long as the satellite is within the line of sight, you can transmit to it. Okay? And each satellite can receive from possibly more than one transmitter. Again, as long as they're within the line of sight, you can receive. It can perform some coding and then broadcast the signal. Okay? For the ground receiver, each one of them can receive from more than one satellite, as long as they are within the line of sight, and decode the messages it wants. Okay, so this is something which is quite different from what we do in existing satellite communication systems, because in existing satellite communication systems, what the satellite does is nothing but store and forward. Okay? Now, if you want to model this as a network, this is what it looks like. You have, for example, we have 3 ground transmitters, X, Y, and Z. Okay? They are connected to the satellites in this fashion. And this layer of nodes is just a dummy node that force the outputs from this node to be the same, okay, because of the broadcasting nature of a satellite. So the ground receivers have some arbitrary access to these satellites according to which satellite is within the line of sight, and they may have different reconstruction requirements. Some of them may want to reconstruct all X, Y, and Z. Some of them may want to reconstruct Y and Z. Okay, so you have some arbitrary reconstruction requirement, and we want to ask the question: what are the necessary bandwidth that you need for the broadcasting? Okay, so this was the problem that we look into. So in this work by Zhang and myself, we obtained inner and outer bound on the network capacity. Okay, and these bounds heavily involve the region of all entropy functions, which is commonly denoted by gamma star. And the rest of this tutorial is to give a high-level description of what's happening, and also I try to get into some subtleties in the technicalities involved. Okay, this is the problem formulation for multi-source network coding. It is on an acyclic graph. Okay, here we let G be an acyclic graph denoted by V and E. As usual, V is the set of all nodes, and E is the set of all edges. S is the set of information. S is the set of source nodes. Where S is a subset of V. Okay, these are the nodes at which information sources are generated, and we let X sub S be this is small s. Okay, be the information source generated at source node S. Okay, and we further assume that these information sources are mutually independent, and the rate of source S is denoted by omega S, okay, which means that the size of the alphabet for source S is 2 to the power n times omega S. Okay. And we also have a set of sync nodes denoted by T. Okay. At each of these sync nodes, you are to reconstruct a subset of the sources. Specifically, we use beta T to denote this subset. So X sub beta T is received as sync node T. Okay. Beta T is the subset of information sources that you want to reconstruct at node T. And there's a rate constraint, R sub E, on each channel E. Okay, so this is the setup of the problem. So with this setup, we're interested in knowing what rate tuples are possible, okay, with the graph given and also the rate constraints given on all the channels. Now, this is a very special class of multi-user information theory problems to look at for the following reason. Okay? Now, most classical multi-user source coding problems become easy, quote-unquote easy, okay, by today's standard, if perfect reconstruction of the information sources is required, and also if the information sources are independent. Then under these situations, then the problems most of the problems are solved, okay, with known techniques. Now, but another thing is that for classical multi-user source coding problems, solutions to these problems are usually very problem specific. Okay, but the multi-source network coding problem do not have such characteristics. Specifically, we require that perfect reconstruction at each of the receiving nodes, although you require only a subset of the sources. Okay, but it's perfect reconstruction, and we also assume that information sources are independent. But still, the problem turns out not to be trivial at all. Okay, and also that for this class of problems, it turns out that for many different configurations, it is possible to put the solution on a rather general setting. Okay, this is something we are going to see. So, which means that you don't deal with one problem at a time. Okay. Now, in 2006, Zhang et al. Refers to myself and Ning Chai, my long-term collaborator. We did a work for the inner bound for the zero-error acyclic multi-source network coding problem. Okay, zero error means that as opposed to arbitrarily small probability of decoding error. Okay, now and then in 2007, we talked about this in ISIT. We obtained a network capacity for the acyclic multi-source network coding problem for arbitrarily small error. Now, the rest of the tutorial will be devoted to how this inner bound and outer bound, and eventually the network capacity were developed. Okay, now we have a pretty general problem to solve, and the simplest case of this problem is the point-to-point communication situation, and we know the answer. Okay, the answer is that if you want to compress an information source x, then the rate that you need to use is at least equal to the entropy of x. Okay, we know the solution to this very simple situation, but if you just look at the problem this way, it doesn't seem that the solution can be generalized to the network problem. Okay, now one approach to this problem is the following. We want to look at a general problem. We know the solution for a very special case, which doesn't seem to generalize. The approach is that we just take a look at the very special case, and instead of proving the theorem in a smart way, we prove the theorem in a stupid way. Okay, and hopefully the stupid way, which has a more elaborate structure, can be generalized to for the general problem. Okay, this is what we're going to do. So the first thing to do is to take a second look at the source coding theorem by Shannon. Okay, before we move on to that, I would like to introduce some definition and also notation. This is called strong typicality, which should be familiar to most people. Now, the definition of strong typicality that I'm going to use is this one. Okay, here n small x semicolon x is the number of occurrences of small x in the vector x of length n. And when you divide this by n, this is the relative frequency of the occurrence of the symbol small x. And here we are to compare the relative frequency with the true probability, and then you take the absolute value, and then we sum it over all x, and this has to be less than or equal to some delta. Now, this is not the definition of strong typicality that you have seen, that many of you have seen before, because in the past, the authors usually write this as different inequalities for each symbol. Okay, but for finite alphabet, this actually is saying the same thing. If the sum is small, then each individual absolute value is small, and vice versa. But it turns out that this form has not only has a notational advantage, but it also paves the way to generalize the notion of strong typicality to countably infinite alphabet, as I would mention in a moment. Okay. Now, so with this notation, we have some very convenient properties. The first one being consistency. For example, if x and y are jointly typical with respect to the generic distribution for x and y, then x is typical with respect to its own marginal distribution, and so does the y vector. And we also have the preservation property, which says that if we start with a random variable x, and y is a function of x. Okay. Now, if x is typical with respect to the marginal distribution of the random variable x, then if you take the function f on each of the component, okay, and then obtain a y vector, then this y vector would be typical with respect to the distribution of random variable y. Okay, so this is very convenient. Okay, now let's take a look at the source coding theorem. The source coding theorem says that R1A is the rate constraint from node 1 to node A, and it has to be bigger than omega 1, that is the rate of the source generated at node 1. Okay, whether that is bigger than or equal to or bigger than depends on how you make the definition. Now, here I'm going to give a dumb characterization of the problem by introducing two auxiliary random variables. In information theory, auxiliary random variable means random variables that do not exist in the original problem description. Okay? Now, these auxiliary random variables are y1 and u1a. Roughly speaking, you can think of y1 being a random variable representing the information source x1. You think of it as a proxy. Okay? And u1a is the random variable that you send from node 1 to node A. Okay? So the requirement for these auxiliary random variables are, first, entropy of y1 is bigger than omega 1, which means that the entropy of the proxy random variable should be bigger than the rate of the source of the generated at node 1. Okay? Now the second requirement is that the entropy of u1a given y1 is equal to 0, which means that what you send out on the link should be a function of the information source, okay, or the proxy of the information source. And the entropy of this variable representing what you send on the channel must be upper bounded by the rate constraint R1A. Okay? And then finally, the entropy of y1 given u1a is equal to 0 says that the y1 must be reconstructible from u1a, y1 being the proxy of the information source. And as we are going to see, once you can recover y1, you can also recover the source. Okay, I'm going to give you an illustration on that. Now, this is the notation we are going to use over and over again, because here this constraint says that u1a is a function of y1, so we are going to write u1a as small u1a of y1. Okay, and likewise, y1 for this constraint, it says that y1 is a function of u1a, so we write y1 equal to small y1 of u1a, where u1a and y1a are just an inverse function of each other. So let's take a look at how we make use of these auxiliary random variables. So we have a message I with rate omega 1. Okay. So now first we generate a random code book. For I between 1 and 2 to the power n omega 1, we generate, for each I, we generate an n-length vector y1 of I according to Pn of y1. Okay, so we use the distribution of the auxiliary random variable, and then we generate an n vector for each I. Okay, so with probability tending to 1 as n goes to infinity, okay, these vectors that we generate, okay, there are 2 to the power n omega 1 of them, are most likely to be typical by the asymptotic equipartition property. And also they are distinct by the fact that the entropy of y1 is strictly bigger than omega 1. This actually has something to do with the channel coding theorem, okay, also by Shannon, because if you use a random variable y1, which is this is the number of vectors that you generate, 2 to the power n omega 1. As long as omega 1 is strictly less than the entropy of y1, then most likely these vectors are distinct. Okay, this is essentially the spirit of the channel coding theorem. Okay, so what we do is after you have generated these 2 to the power n omega 1 y vectors, what you do is if the message I comes up, you map it to this vector. Okay, and then after mapping it to this vector, we take the function u1a on each of the components. So okay. Now by the preservation property of strong typicality, this is going to be typical. This vector is going to be typical with respect to the distribution of u1a. Okay. Now here I'm still confining myself to strong typicality, which means that the auxiliary random variables that you choose from needs to be of finite alphabet. Okay. Later on, I'm going to relax that constraint. Okay. So after generating this vector here, which is most likely to be typical, we send the index of this vector in the typical set. Okay. Now this is going to take a rate less than R1A plus some small quantity eta, because the size of the typical set U1A is upper bounded by 2 to the power n times the entropy of U1A plus some small quantity. And we assume that the entropy of U1A is less than R1A. That's why the rate that you need to use is upper bounded by R1A plus some small quantity. Now in information theory, it is always important to think in a sloppy manner, to ignore those rare events to start with, and then we try to fix the epsilons and deltas at the end. Okay, now this index is being sent through the channel at a rate that we are happy with. Now, so this is the receive vector, and then after receiving so you know the index in the typical set, and then upon getting the index, you know the vector. Okay, and so essentially, what you get what you get here is the same as what you get here, except for some small probability. Okay? Now with this vector, we apply the function y1, which is the inverse function, to this vector on a component-wise. And because y1 and u1a are just the inverse function of each other, you recover y1i. And because the y1i's are most likely to be distinct, once you receive the vector y1i, you can tell what is I, okay, with very high probability. So this is essentially the situation. So this shows how we use these auxiliary random variables to characterize the problem, not in the most clever way, but in a dumb way. But this turns out to be very powerful. Now here's a more elaborate example. So in this case, we have two source nodes, 1 and 2. Okay. So the random variables that represent the covert transmit on the link is denoted accordingly. For example, from A to B, we denote this by UAB, so on and so forth. In this case, x1 is generated here, x2 is generated here, and x is to be reproduced here. X1 is to be reproduced here, and x1 and x2 to be reproduced here. Okay? So as I said, we need auxiliary random variables to as a proxy for x1, and this is y1 here, and then for x2 we have a proxy random variable y2, and together with these two proxy random variables, we have an auxiliary random variable for each channel. So an information rate pair that is achievable is being characterized by a set of constraints like this. Okay, the constraint is that if there exists auxiliary random variables ys for each source S and ue for each channel E, such that hy1, y2 is equal to hy1 plus hy2. Because we are talking about two information sources that are statistically independent, we also require the two proxy random variables to be independent. Okay? And we require that hys is bigger than omega s. This is essential because we need the proxy random variable to have enough entropy to cover the information source. Okay? And this is the rate of the information source S. And then we have these encoding requirement, meaning that the output of a node has to be a function of the input, okay, as we would expect. And we also need entropy of UE less than RE. This is not to violate the rate constraint. And then at the bottom, we have these reconstruction requirements. Okay. So once you have seen the first example, you would have no problem writing down the constraints for the second example. Now, for the random coding, it is very similar to the point-to-point case, except that I would like to make a few remarks. Okay, so now we have more than one source node. Okay, let's say we use I to index the message from source node 1, and we use J to index the message from source node 2. So for message I, you map it to a vector y1 of I. For message J, you map it to a vector y2 of J. And now here's the key point. In fact, this is the very reason why in the first place we assume that y1 and y2 are independent. And this is to make the problems solvable. Okay? Now, because y1 and y2 are independent, if you generate y1a and y2a locally, y1i and y2j locally, most likely they would be jointly typical. Okay? If x1 and x2 are not independent, if you generate the two random cohorts locally, most likely they would not be typical. Okay? But we need joint typicality in this case. Now, because all the random cohorts generated at the source nodes are jointly typical to start with, and when you progress through the network by applying a function to the vector on a component basis, by the preservation property, this would be able to maintain joint typicality throughout the network. Okay? In particular, at the inputs of a sync node, which is essential because if all the incoming vectors to a sync node are jointly typical, then you apply the decoding function component-wise. That would allow you to decode properly. Okay? Now, one thing I would need to say is that the error probability analysis is somewhat more complicated because we are talking about decoding more than one index at the same time. Okay, but it can be done. Okay, essentially, so the main thing is that you start with something that is jointly typical, and then you do it component-wise, and that would be able to maintain a joint typicality. Okay. Now, we talk about an inner bound for general acyclic networks. Yes. So is your condition, is it only sufficient right now, or is it necessary? It's only sufficient. In fact, But the essential techniques was can be found in the a paper by Zhang and myself on the telecommunication network. Okay, but the bounds were there's a gap between the inner bound and outer bound, and it took us quite a long time to be able to fix it. Okay, in the paper with Ning Chai and also in Zhang in 2006, we instead of dealing with arbitrarily small probability of decoding error, we dealt with the zero error problem. And again, that was an inner bound. I'll make a remark on the zero error case at the end of the talk. Okay, so the inner bound, for the general inner bound would be something you would expect. Okay, we let R prime be the set of all information rate tuples omega. This is a bold-faced omega. Such that there exist auxiliary random variables ys for each source S and UE for each channel E, which satisfies the following conditions. The first condition is that all the proxy information source variables are statistically independent. Okay. The second one is that you must have enough entropy. Okay, the proxy random variables must have enough entropy. And the third constraint says that for the source node, the output from that node must be a function of the proxy random variable ys. And then within the network, we must have the output variables from node I. I'm sorry that I'm reusing the index I. Given the input variable in I, okay, is equal to 0, which means that it is a function. And then the entropy of the auxiliary random variable for channel E must be upper bounded by the rate constraint. And finally, those information sources that you want to recover must be a function of all the incoming auxiliary random variables at each sync node. Okay. And we let R be this is R prime. R prime is defined by this, and then we let R be the capacity region. And then it turns out that R in, which is defined as the convex closure of this region R prime, is indeed an inner bound to the capacity region R. Okay. Now, the next thing I want to do is to recast this R in. This R in, as I stated here, is in a form which is familiar to many who are proficient in multi-user information theory. But I'm going to recast this into a form which links the study of entropy functions, okay, that started in the late 90s. Now, here's the setup. We let script n be a collection of discrete random variables with unspecified joint distribution. Okay, you only have a collection of random variables. I haven't told you what the joint distributions are. And we let Qn be the power set of script n minus the empty set. Okay, so the size of this is 2 to the power the size of n minus 1. Okay, now we considered the Euclidean space of this number of dimensions, okay, with the coordinates labeled by small h of A, where A is a subset of power set of Qn. So the idea is that suppose we have 3 random variables, okay, then we would have 7 joint entropies, okay, 2 to the power 3 minus 1, because we take away the empty set, okay, and this thing here, script h of n, would refer to the 7-dimensional Euclidean space where each coordinate labels a joint entropy. So the 7 joint entropies are the entropy of the individual random variables, the joint entropy of 2 random variables, and the joint entropy of 3 random variables. Okay, so here we are talking about a 7-dimensional space with the axis or the coordinates representing the entropies. Okay. Now, we say that a vector is entropic, okay, if it corresponds to an entropy function. Now, in this 7-dimensional Euclidean space, to fix the idea, I'll let the number of random variables to 3, okay, to be 3. And in this 7-dimensional space, if you pick any point, it it may not correspond to an entropy function. Okay, for a point to be qualified as an entropy function, you must be able to find a corresponding joint distribution for 3 random variables such that when you evaluate the values of the 7 joint entropies, it is exactly that point. Okay. Now, and then we define gamma n star to be the set of all entropic functions in the Euclidean space. Okay. Now, it turns out that this region gamma n star is non-convex in general. Okay, it has a very complicated structure. But if you take the closure of it, it is convex. Okay. Now, we know that one can easily obtain an outer bound on gamma n star because we know that for every joint entropy function, if you evaluate all the corresponding or the associated Shannon information measures, they're always non-negative. Okay, so each of these Shannon information measures, for example, mutual information of between x and y can be written as hx plus hy minus hxy. Okay, and this is always bigger than or equal to 0. And in this Euclidean space, it is nothing. Each of these inequality that we are very familiar with, okay, the non-negativity of Shannon's information measures, are just hyperplanes in this Euclidean space. Okay. So and we denote this region, namely the intersection of all the half spaces corresponding to the non-negativity of Shannon's information measures by gamma n. Okay, I'm sorry that I don't get into the details here because I really need to get to the heart of the problem quickly. Otherwise, we won't be able to have a banquet this evening. Okay, so geometrically, this region is all bounded by this region, okay, induced by the non-negativity of Shannon's information measures. And one thing I would like to say about non-Shannon-type inequalities is that they exist. Okay, there exist additional constraints on gamma n star bar. Okay, in addition to those inequalities corresponding to the non-negativity of Shannon's information measures, and these are called non-Shannon-type inequalities. Right? Okay, now we are going to cast the region R in that I have previously defined for you in terms of gamma star. Now, in this setup, we let n be the collection of all the auxiliary random variables in the problem. Okay, ys being the proxy random variables for the information sources, and the ue is the auxiliary random variable for the channels. And to simplify our notation, we are going to use this. Let's a and a prime be subsets of this one. Okay, this is an element of the power set. Okay, we define ha given a prime is equal to ha prime minus ha prime. So you can essentially think of this as the conditional entropy of a given a prime is equal to the joint entropy of a and a prime minus the entropy of a prime. Okay, essentially it is just like that. So and then we let our so our prime can be described in a different way in terms of this region gamma n star. Okay, we let R prime be the set of all information rate tuples omega such that there exists an entropy vector, okay, in this region satisfying hys is equal to summation hys summing over all s, and then hys is bigger than omega s for all source s, and then h of all u out of s given ys is equal to 0. This is the and h of u out I given u in I is equal to 0. These two are the encoding constraint. Okay, namely that the output of the encoder must be a function of the input of the encoder. And then we have this rate constraint, h of u e less than r e, the rate constraint for channel E. And then finally, we have this reconstruction requirement. So nothing has changed except that we're using a different language. But it turns out that this allows us to manipulate the problem in a totally different way. Okay, Now, I finished talking about the inner bound, and I'll talk about the outer bound. Okay, the outer bound is essentially the same thing as the inner bound, except for something I have put in red. Okay, here for okay, now you define this region R prime, and then you take the convex closure and make it into R in. Okay, now here there exists H in the gamma n star, okay, without a bar. Okay, in the outer bound, this is replaced by gamma n star bar. You take the closure. Right? So this one difference between the inner bound and the outer bound. And another difference is that for here and here, for the inner bound, the inequality is strict, while here for the outer bound, the inequality are non-strict. Okay. Now these two regions are different because for a general region, if you don't know its topological structure, if you take the closure first and then you take projection or take intersection, it is different from taking intersection first and then you take closure. Okay, this is essentially why the inner bound and outer bound are not obviously the same. Right? Okay, now it can be proved that this is an outer bound. I'm going to show you how it can be done. First, in the using the standard techniques, but after some point you have to use some other techniques. Okay? Now using standard techniques, it can be shown that well, of course, the first line is by assumption. We assume that all the information sources are independent. Okay? And then we can show that and then it can be shown that the entropy of Hs is bigger than or equal to n times omega s minus some small quantity. Okay, given a code, we can show that this is true, and these two are true by construction because of the existence of the code. And then we, as usual, we have entropy of UE is less than or equal to, this is the n times RE plus some small quantity. Okay, this is the random variable representing the code word that you send on the channel. And then we have this, for the reconstruction, we have entropy of x beta I given U in I is less than or equal to some small quantity. Okay, where this small quantity goes to 0 as n goes to infinity and epsilon goes to infinity. Okay. So when n goes to infinity and epsilon goes to infinity, both this one and this one and this one goes to 0. Right? So this is nothing very complicated. Now by letting ys equal to xs, okay, ys is the auxiliary random variable we are looking for when we prove the converse coding theorem. All you do is you just substitute ys by xs, okay, from here, okay, and so we see that now this is this form is in a form which is familiar to all of us who knows information theory. Okay, the converse proofs goes like this, okay, for most problems. Now and then we now by letting ys equal to xs, we would be able to cast all these things in terms of gamma n star. Okay. Now, what you do is you just replace xs by ys, and then you replace the capital H by the small h, and nothing else. Okay, nothing special so far. Right. And then something interesting comes up. Okay. Now we recall that gamma n star bar, the set of all entropy functions after taking the closure, is a convex cone, and therefore, if H is an entropy vector, if you scale it down by a factor of n, it may not be in the region, which means that it may not be an entropy vector, but it is an element in the closure of the set of all entropy vectors. Right? Now, therefore, if you start from here, from this set of constraints, if you divide everything by n, okay, we see that there exists an H in gamma n star bar. Okay, you need the bar because we only know that this is by taking a closure, it is a convex cone. Okay, then you get this. This is nothing different from what we had before, except that you just divide things by n. Okay, so when you divide things by n, you have this 1 over n times h of ys. Okay, and then you rename it as h of ys. That's it. Okay, we haven't changed anything. Now, to complete the proof, it seems that you only need to let n goes to infinity and epsilon goes to 0. Okay. In fact, I missed a very important point after writing this up a few times until I wrote up my second textbook. Okay. And then when I wrote this up, I realized that I missed a very important point. Here, what you really have to do is to realize that the last step actually invokes the fact that you are taking the intersection of a series of monotonically decreasing compact set. Okay, so you take you have a series of set that you want to take intersection, and each one is smaller than the previous one. Okay, and if the sets are not compact, then after taking the intersection of this countably infinite set, it may be empty. Okay, to guarantee that the intersection of this set is non-empty, you really have to show that actually all these sets that you're taking intersection of are compact sets. Okay, that can be done. Okay, so this is just another lesson that I learned that I tend to be careful in proofs, but even so sometimes I'm sloppy and I may fall into some traps. Now. So we talked about the inner bound and outer bound, and in 3 years ago with Xinjin Yan and a student of Zhang then, and Zhang and myself, and we finally were able to close the gap between the inner bound and the outer bound. And this is one thing I would like to mention is that the expression for the network capacity that we published in the proceeding was not the right one, because subsequently when I wrote up the textbook, I found that there was some problem with it, and we made a correction in the presentation. So when you look at the proceedings, it's not giving the right expression. If the only published version that is correct is the last chapter of my latest textbook. Okay. The journal paper is getting toward the end of the pipeline. Now, I'll give you some flavor of this network capacity region. Okay, here gamma n we have seen gamma n star before. Gamma n star is the set of all achievable entropy functions. Now, gamma n star star is a set of all entropy functions for random variables with finite alphabet. Because we need to find an alphabet in order to use strong typicality for the encoding. Okay. Now, this is the form of the network capacity. So we take this region gamma n star star, we intersect it with some set, which we denote by script L123, which I will explain to you what they are. And then you take the closure. And then you further intersect with another set L4 and another set L5. Okay, you take this thing here, and then you project this region onto the axis corresponding to the proxy random variables representing the information sources. Because out of this big soup of random variables, we are particularly interested in what information rates are achievable and what information rates are not achievable. That's why we need to project them onto this collection of axes. Okay. And then after doing that, we take something which I denote as lambda. Okay. So this is a further elaboration. So this is the reproduction of the expression. Now, L123 is a subset of this space, the Euclidean space, corresponding to the following equality constraints. First, the the proxy information source random variables are independent. Second, the output variables given the source random variables are the conditional entropy is equal to 0. And third, the conditional entropy of the output given any input of an intermediate node is equal to 0. Okay. Now, so this L123 is just a collection of hyperplanes. Okay, cutting through the origin. Okay. And L5 is a subset of this Euclidean space corresponding to the equality constraint for the reconstruction requirement. Okay. Again, this is a collection of hyperplanes passing through the origin. So one important reason why we want to invoke this gamma n star thing is to be able to look at the solution in a geometric way. Okay. Now, and then what is L4? L4 is the subset of the Euclidean space corresponding to the inequality constraints for the rate constraint. Okay, the entropy of UE, which is the auxiliary random variables for channel E, is upper bounded by the rate constraint RE. And then, so this projection YS is to project, this whole thing. Okay, it's very high dimensional thing into a dimension which is equal to the number of information sources. Okay, you do this projection, and then finally you will take this operation lambda, and this lambda, if you put a set here as the parameter, lambda on this set A simply takes all the vectors in the non-negative orthant inferior to at least one vector in A, which means that if a particular rate tuple is achievable, then any tuple inferior to that rate tuple is also achievable. Okay, this essentially says that. Okay, now this is a implicit characterization of the capacity region in the following sense. Now, for details, the only published version is the last chapter of my book. Now, one remark I would like to make before we proceed is the following. Now, things are. I explained to you that the capacity region can be expressed in terms of this thing gamma n star star, which is the entropy function for all random variables with finite alphabet. Okay, so this is not exactly gamma n star that we have spent so much time studying for the last 10 years or so. Okay, now, however, this actually can be rectified with some recent results by Siwei Ho and myself. This actually was in the PhD thesis of Ho, who was my student then. In his thesis, he introduced a notion called unified typicality that works for countable alphabets while preserving the essential asymptotic properties of strong typicality, namely that we have the AEP and also conditional EEP. Okay, and there's also the consistent property. And consistent property means that if x, y is jointly typical, then x is typical and y is typical. Okay? And there's also the preservation property, not as neat as the finite alphabet case, but it holds in an asymptotic case, which is good enough for doing the random coding in this multi-source network coding problem. Okay? In this multi-source network coding problem, essentially, we only need to invoke these three properties. Okay, if these three properties holds, then it goes through. So the reason why we stuck with finite alphabet was that we need to use strong typicality. But now we have a more general notion of unified typicality, which have the same property. Okay, so we can, instead of using strong typicality, we can use unified typicality and hence replace gamma n star star by gamma n. Okay, so that is we remove the the constraint that the alphabet size needs to be finite. Okay. All right, this is essentially what I just said. Okay. Now I'd like to make a remark on make some remarks on the nature of the characterization. Now, this is this characterization in terms of gamma n star is a single-letter characterization. Okay. But because but there's no bounds on the alphabet size. Okay. In multi-user information theory, if you have no bound on the alphabet size, you cannot evaluate the region. Okay. In this case, we also don't have the bounds on the alphabet size, so we cannot evaluate the region, and therefore I would call this an implicit characterization. Okay. Now, this although we don't have bounds on the alphabet size, this characterization is actually quite useful, because if you get better inner bound or outer bound on gamma n star, then you can immediately have a better inner and outer bound on R. Okay, so if you have a better understanding on the problem of entropy functions, then you get a better bound for this problem. In fact, as a matter of fact, these two problems are the same, as I'm going to tell you. So in particular, if we replace gamma n star by gamma n, okay, which is the region induced by the non-negativity of all Shannon's information measures, which is an outer bound on gamma n star, then you would be able to obtain a region for an outer bound on the capacitive region, which is computable. Okay. So, and in fact, RLP, where RLP stands for linear programming, is known to be tight for some special cases. Now, I'd like to make some remarks on the role of non-Shannon-type inequalities to this problem. Doherty, Freiding, and Ziegler in 2007 gave the first example of a multi-source network coding problem that requires this non-Shannon-type inequality that we discovered in '98 to characterize the capacitive region. Okay, this is a very significant result, because when we discovered that non-Shannon-type inequality, we were hoping that it would help us to solve some open problem, but we waited and couldn't find that problem until Ken Ziegler and his friends were able to find such a problem. And shortly after that, and independently by Terence Chen and Eric Grant, using a totally different technique, showed that every entropy function actually corresponds to a multi-source network coding problem. Okay? And the implication is that every non-Shannon-type inequality, be it known or yet to be discovered, would be useful in some multi-source network coding problem. Okay? Now, the conclusion is that together with our characterization of the capacitive region in terms of gamma n star, the conclusion is that the determination of gamma n star and multi-source network coding problems are almost equally difficult. Actually, one can say that they are exactly the same problem. If you can solve one problem, you can solve the other problem, and vice versa. Okay. So the connection between the study of entropy function and multi-source network coding problem actually is tighter than we expected. Okay, here are some further issues. For the zero-error multi-source network coding problem that was studied by Zhang, myself, and Tai in 2006, the conventional converse proving technique doesn't work. Okay, the main idea was of the zero-error coding was that I mentioned that because the information sources are linearly independent, if they are for the proxy, you use the proxy random variables to generate the code book, okay? And most likely the vectors that you generate are jointly typical, okay? If they're jointly typical, then everything will go through as expected. But if they're not jointly typical, in order to achieve zero error, you have to take care of them. And by with this, you just encode them as a special case with using a longer code word. Okay, that accounts for the variability of the code word length, and this is a variable length code. Okay, it turns out that for variable length codes, things are much more complicated. For point-to-point communication from one point to another point, if you send a variable length code through, it still observes the entropy bound. Okay, the expected length of the code word is lower bounded by the entropy. Okay. However, it turns out that even for two channels, okay, you have a source node and a sink node, and in between you have two channels, sending a pair of code words through, which is decodable at the other end with zero error. It turns out that if you look at just one channel, the entropy bound may not be observed. Therefore, for variable length multi-source network codes, when you prove the converse coding theorem, you simply cannot apply the entropy bound. Therefore, we don't have a converse proof, okay, for variable length network codes. And therefore, we were motivated to study multi-channel zero-error source coding. That was the work that I presented at the ITW in Cairo just last month. Okay, and this was joint work with Yao, who is a visiting student from Tsinghua. Okay. Now, having said that, so the remaining issues to be resolved are zero-error multi-source network coding. But having said that, I have only confined myself to the discussion of acyclic networks. Okay, for acyclic networks, we know what to do. We know how to do the coding in an order consistent with the partial order of the graph. But for cyclic networks, we have very little idea what can be done in general. So I would call this the holy grail for multi-source network coding. So that concludes my talk. We have time for several questions.
So there has been some work, on characterizing domain as well, like using the quasi-uniform distribution, so on and so forth. So can you tell us a little, what's the state of the art?
The quasi-uniform variables.
Distributions.
Yeah. Well, this actually has something to do with the plenary talk that I gave at Seoul. Okay, namely that's the right now we know that the entropy function, the homograph complexity, some inequalities related to finite groups and their subgroups, and also network coding, they share the same structure. Okay, that's actually points to the question that you raised. Okay, it is the same structure, but we don't understand what exactly is the underlying structure. So that's something we know it can be done, but what it exactly means we just don't know. Oh, actually, no. Another thing is that a combinatorial structure, okay, which we call the quasi-uniform structure. Okay, that it has something to do with that. So a few things: a certain combinatorial problem, some inequalities in group theory, network coding, homograph complexity, the entropy function. They all share the same structure. Yeah, I think so. But so far we know only very special cases. Even the multiple unicast case don't seem to have a neat characterization.
Also, is it easier to test whether one particular point lies in that set in any way, rather than trying to characterize the whole region?
That I don't know. I mean, if you can do it, you have an implicit solution to the problem. Whether it is actually easier to test the point than to characterize the whole region, I don't know. Removing every vector which is matroidal, correct. But let me see. But no. Actually, no. There are entropy vectors that are not a matroid. That are. Oh, I'm sorry. Moving those vectors that are not you mean not representable?
Yeah, but no. My question is just a vector which is entropic. It better first satisfies the inequalities of matroids.
It's a polymatroid.
Yeah. So indeed, then my question was regarding representation of matroids. So if the vector is satisfying the inequalities of a matroid which is representable over a finite field, then do we know that it is entropic?
No, actually, there's still a gap. For example, we know that for every representable matroid, the Ingleton inequality is satisfied. Okay. However, there exist entropy functions that does not satisfy the Ingleton inequality. So what the general picture is that if you think of if you want to for this, at least for this problem, if you want to consider all possible codes, then the gamma n star is the thing to look at. If you want to consider all linear codes, then you look at all representable matroids. Okay, but there's a gap. There's a gap between them, which means that there's certain situations that you must use nonlinear codes, and that was shown by some previous authors, including the group of Ziegler and Doherty, Freiling, and Ziegler.
So there's not a formulation that tells us what matroid we have to look at?
It is a subclass. Yeah. It is a subclass.
The calculation is also open.
The calculation, to my knowledge, Doherty, Freiling, and Ziegler has been able to characterize it up to 5 vectors, but using a supercomputer. And for 6 vectors, it's wide open. But even for 4 vectors, the usual polymatroidal inequalities together with the Ingleton inequalities are necessary and sufficient. But for 5 vectors, no.
Is there any other question from the audience? No? Let's thank Raymond once again.